Okay, so to summarize, we covered MDPs, Markov decision processes, which are defined as states, actions, as a set of states, a set of actions, a reward function, and transition probabilities. And sometimes the initial state, again, sometimes state's important, sometimes it's not. Specifically, it's more relevant in reinforcement learning. But it's not relevant, the initial states are not relevant to define pi star. That is, for running value iteration or policy iteration, we don't need to know an initial state. It doesn't matter. It won't change our computation. We saw that meaningful policy evaluation requires a discount factor, right? We discussed that. That's we'll just explode to infinity. We might exploit to infinity, unless we have a finite planning horizon. Right? If we're allowed to continue in the environment to infinity, then we have to have a discount factor. Or we could have terminal states and avoid the discount factor. That's also a possibility, but we'll have to guarantee that any trajectory will eventually arrive at terminal state. There are some conditions. If you went over Markov chains, you probably went over these conditions for convergence. For the sake of our course, for our purposes, we'll simply assume that we have a discount factor. Okay, for all cases, we just assume some discount factor. If we assume to know the MDP model and reward function, it will allow us to compute the optimal policy offline. Offline meaning without interacting with the environment. We know everything. Then we can do offline optimization using value iteration, VI, or policy iteration, PI. Right? We saw these. These are offline approaches. Policy iteration is usually faster to converge due to simplified Bellman updates. That is, they allow us to eliminate the max A operator, and then we get a linear set of equations. Actually, it's more than that. It's also because policy iteration has a very specific stopping criteria, which tells us when the policy has converged, unlike value iteration. Next, a known model is not a practical assumption and is not assumed in general reinforcement learning. And so we are going to drop this assumption in the next lecture. But still, it's very important, all of the material that we covered through this lecture, because this will form the basis towards online reinforcement learning approaches. We will use policy-based approaches and value-based approaches, and we'll combine them. So we're just going to extend the offline methods that we've seen today. What next? So next, we're going to start to discuss reinforcement learning approaches. The first, I would say, a more simple approach that we're going to see for reinforcement learning, online reinforcement learning, is a Monte Carlo approaches, Monte Carlo reinforcement learning algorithms. We'll discuss this in the next lecture. Regarding assignments, so at this point you are ready to start implementing value iteration, asynchronous value iteration, policy iteration, and these three algorithms, again, available in through the course website, are due by, please see Canvas for the exact dates. Okay? And these will be, you will submit those through Canvas. Also, there is a quiz available on Canvas regarding dynamic programming, whatever we covered in this lecture. And regarding the course project, please find a partner and start converging or deciding what would be your project topic. Specifically, if you have some problem that you're working on in your own research, that would be a great topic to work on. Just try to see if your problem is appropriate to be solved with reinforcement learning. And if so, please define the relevant MDP, to represent your problem, right? And see that it actually has a transition probabilities. It's it's not deterministic, and that the process is Markovian. That is, at each state, there is the optimal action to take is independent of the states that we visited previously. That's it. Any questions? None. Okay. Thank you.